what we are really doing is taking DOM spaces. So we can also define this map here, just saying that instead of thinking of vectors of length epsilon, we are going to think of vectors of length 1. We're going to transform those little vectors that we have here of length epsilon on each side of the manifold. We're going to consider them of length 1, and that's just considering a DOM space. So what that second map is doing, this map here is doing, is just, well, it's just a multiplication, rescaling those vectors. And then, if we compare these two maps, the map C, mapping the n plus r dimensional sphere into that, into this, I'm not going to read it aloud, and comparing it with this, then we get this. We get a map from the n plus r dimensional sphere to the DOM space of the normal bundle of M. You see comparison, it's important. So now we have our map. This we had from the previous slide. And we know from before that we have already met that these DOM spaces of the normal bundle on M, well, we can think of the inclusion of M, of the embedding of M into the Grassmann manifold. So we can also think of the DOM spaces of the normal bundle going into the bundle going into the universal bundle, the DOM spaces. So we have that we can continue comparison maps from this to this, and as we saw before, we can let n go to infinity, and then in the end, after many mappings, we come to this. So what we have in the end is a map from the n plus r dimensional sphere into TBOR, and that's already defining a map in our stable homotopy of TBR. So we have already the definition of the element, but that's not quite convincing, because we have made several choices. Well, along the way, I've said that we had an equivalence class of manifolds, and then I picked one, and then I also chose some embedding, and so on and so on. So to be completely convinced that this definition of the element theta is correct, I should need to say why it is independent of those choices that I have been doing along the way. So first of all, I chose a tubular neighborhood that I wrote down as epsilon. Well, now I'm going to say that in the dependence of choice. Why? Well, because choosing another value of epsilon, does not change the homotopy class. Of theta. So that's fine. And we also had a choice of embedding of M into R. So we also need independence of choice of embedding. embeddings of m plus 1 and see if it works. Well, we need to find a homotopy between these two. If we can do that, then we are safe. So, well, the space is highly connected, so in particular it's path connected, so there always exists a homotopy between these. We can represent these because we can say m, this should be another m, and then it should be 0 and it should be at 1. If we can see that this embedding of m is homotopy to this other embedding of m. So as they are homotopic, then it doesn't matter which embedding I choose. And lastly, within the equivalence class of coordinate manifolds, I also made a choice of m. So I would need to know if, for example, if I take another, if this is m and this is another m, I should also need to be able to prove that it doesn't matter which one I take. So, well, in some sense it's the same as for the embedding, because we only need to find a homotopy between the maps associated to those manifolds. So, while following the same steps as before, we can construct. Oops, this is very small. This is giving some details, but we can do that. So, in the end, following the same procedure of embeddings into the Grossman manifolds and letting them go to infinity and so on, we can define this map so that the maps associated to both manifolds are indeed homotopic. So the element is also independent of the choice of manifold. So as it is independent of all the choices that I have been doing, then we can be convinced that it is in fact a good definition. And now for the second step. Well, for the second step, we want to show that it is in fact a homomorphism. And well, to do this, well, what we want to show is in fact what I have there, that the map, well, you have it there. So what we want to do is, well, we have two embeddings of M1 and M2, and we have them embedded in two different paths of R, N plus R. So what we want to do is choose tubular neighborhoods, just as we did before, but we are going to be careful so that those neighborhoods still remain within the same half of the plane. So you see that M2 is embedded in R plus, and then it's the hyperplane, and M1 is embedded in the other part of R plus, I mean R minus. And well, these two embeddings, we choose tubular neighborhoods that remain within the same part of in the same side of the hyperplane. So we can collapse the sphere, what we have our map, from the N plus R sphere to TBR. So, well, we can collapse, this is a very usual, very normal collapsing map. And then from this wedge sum of two spheres, we can use our theta M1 plus theta M2 to map to TBR. So indeed it's exactly the same map as we saw before, only just that now we are working on a wedge sum of two different spheres. And that's why we wanted the tubular neighborhoods of M1 and the tubular neighborhood of M2 to lie in two different half planes so that they fit together. And well, we are done, because this is exactly the same map as is defined by the homotopy classes. So it's indeed a homomorphism. So now it remains to show two things: that the homomorphism is surjective, and also that it is injective. So for the third step, we will try to show that our map theta is surjective. Well, we start by noting that what we had before, our maps is going from the n plus r dimensional sphere into DDR, and we note that well, this sphere is compact, so we can find any open cover. So that for any open cover, we can find a finite subcover. So that means that that map acting on the sphere can be included in the Dom space of that universal bundle. But do note that what I'm writing here is an S. So now it's hard work. Now it's hard work because we need to homotope the map of the n plus r sphere into this Dom space to a new homotopic map satisfying several conditions. And well, the new homotopic map needs to be differentiable on a neighborhood of the Grassmann manifold. And very, very important is that it must also be transverse regular. Well, we have already seen a few minutes ago what transverse means.